So the next one we're going to look at here is the thyroid hormones. We have a couple of hormones that we're going to be looking at. We're going to be primarily looking at the hormones coming from the colloid and follicular region of the thyroid here. So the hormones that are coming from the follicular region of the thyroid are going to be diiodo and triiodo and tetraiodothyronine. These will be abbreviated as T2 diiodo, T3 triiodo, and T4 tetraiodo. Now, the way in which this gets assembled is that we're basically going to be taking a tyrosine molecule and iodating the tyrosine molecule, forming the monoiodine. That monoiodine will then combine with a secondary monoiodine to form a diiodo or a T2 molecule. The T2 molecules can interact with each other to form the T4. The T1 or the monoiodo and the T2, the diiodo, can combine together to form the T3. The T3 can combine with the T1 or the monoiodo to form the T4. The follicular cells are going to be secreting and absorbing these thyroid hormones during the synthesis process. Part of the regulation of the glandular function here is the concentration of iodine within the diet, in which the follicular cells will continue to trap and attempt to produce the monoiodine form of the molecule when iodine concentrations are low, leading to the formation of what is usually referred to as a goiter for people who have low iodine in their diet. Now, what's interesting is that the tissues themselves will be converting the T4 to the T3 form. The T3 will be the principal functional form of the thyroid hormone. T4 will be used more readily during growth phases and in fetal development, whereas T3 will be used predominantly throughout the rest of the physiological regulation. So let's take a look at what's going to end up regulating the thyroid hormones and regulating some of the metabolic issues going on with the body. So there are going to be a couple of signals that are going to come into play here. One is going to be the regular low signals of T3, T4. But we also have a secondary signal and the principal regulator on metabolism coming into play, leptin. Whereas leptin starts to diminish as an indication of large amounts of energy reserves and large amounts of lipids being produced for use by the tissues. A secondary signal that's going to come into play is physical and metabolic stress. The physical and metabolic stress combined with low levels of leptin is going to increase metabolic rates independent of any change of the thyroid hormones. We're going to stimulate thyroid releasing hormone from the hypothalamus, which is going to stimulate thyroid stimulating hormone to be released from the pituitary. That thyroid stimulating hormone will immediately inhibit the hypothalamic response to TRH, and we'll head out and we'll stimulate the follicular cells to increase the production and then release of T3 and T4. T3 and T4, as it goes into circulation, will start to inhibit on the follicular cells, and then we'll start to interact with all of the tissues of the body. It's going to increase the aerobic metabolic rate. It's going to increase lipolysis and beta oxidation of those lipids that are going into circulation. It's going to increase uncoupling proteins at the mitochondria to increase thermogenesis. It's going to increase sodium-potassium pump assemblage and integration into membranes, thereby allowing for greater tissue excitability. And it's going to increase anabolic responses. The increase of aerobic metabolism and the increase of lipolysis and uncoupling protein utilization is why the thyroid hormones are mistakenly referenced to as being the basal metabolic rate hormones. They are not the basal metabolic rate hormones. The true basal metabolic rate hormones, leptin, adiponectin, ghrelin, are going to set energy utilization. The thyroid hormones are going to primarily function on the mitochondria, increasing mitochondrial functioning. One of the reasons why people who have a hypothyroidic issue, low thyroid hormones, have greater amounts of adiposity, body fat, is because they lack the signals to increase the lipolysis and they lack the signals for the mitochondrial upregulations. It's also why people who are hyperthyroidic tend to have higher levels of body temperature because of the increase of uncoupling proteins. The people who are hyperthyroidic also tend to have lower levels of body fat, and that's because of the higher amounts of lipolysis. So that's part of what's going on at the thyroid, but coupled with the thyroid is the parathyroid gland. And so we're going to be looking here at what's referred to as the calcium regulation. Now, textbooks like to talk about the calcium regulation as it relates to bone health, but the real reason why we have to regulate calcium is because calcium in the blood is a stimulator for clotting. And so what we're attempting to do is we're attempting to ensure that we have the correct level of calcium in the plasma so that we do not spontaneously clot. In this case, we have antagonistically functioning hormones in which high levels of calcium is going to stimulate the parafollicular cells to release calcitonin. It's also going to inhibit the parathyroid gland. Calcitonin interacting with vitamin D3 is going to increase calcium and phosphate integration into bone tissue. It's going to increase the absorption of calcium at the kidneys. It's going to decrease the absorption of calcium at the intestines. By increasing the absorption of calcium at the kidneys, it increases the excretion rate of calcium. By diminishing the amount of calcium being absorbed at the intestines, it reduces the plasma load of calcium. This is going to diminish the levels of calcium within the blood. If we get too low, we're going to flip the signal here. And what we're going to do is we're going to inhibit the parafollicular cells and we're going to stimulate the parathyroid gland. Stimulating the parathyroid gland is going to increase PTH. By increasing PTH, we're going to diminish the amount of calcium being absorbed at the kidneys and we're going to increase the amount being absorbed at the intestines. By doing that, we diminish the amount of calcium being excreted and we increase the amount that's being absorbed from our diet. At the same time, we're going to stimulate for the release of calcium from calcium deposits, and one of the largest calcium deposits in the body is within the bones. And so we will start to see a change of calcium depositing with the bones to diminish the amount of calcium in the bones. Now, the reason why parathyroid hormone gets linked with osteoporotic changes is because of the misconception of what actually keeps bones healthy, and we will cover that in the use it or lose it part of the musculoskeletal tissues. But it has to do with load on the bones. The bone itself has internal hormonal signals that's going to regulate how dense the bones are based off of whether or not the bones are being used, not parathyroid hormone. So let's start taking a look at stress responses here by looking at the adrenal gland. And the adrenal gland we'll look at in terms of two components here. The cortical component, which is going to be the corticosteroids. Those are the endocrine responses, the long-term responses, and then the medulla responses, which are going to come from the fight or flight, norepinephrine, autonomic nervous system responses. So we're going to start with a stress response here. Now here's the thing, we can't distinguish where that stress is coming from, whether it is real, whether it is physiological, metabolic, or whether it is psychological. That's going to stimulate the hypothalamus to stimulate the sympathetic nervous system. The sympathetic nervous system is going to stimulate the adrenal medulla to increase epinephrine. So that we get the correct level of epinephrine response, we're going to slowly start to reduce the amount of epinephrine coming out. Now here's the thing. We cannot reduce epinephrine low enough because this is functioning on a positive feedback loop. Epinephrine, because it's going to function on the adrenergic receptors, will function everywhere. Cardiovascularly, it's going to lead to a cardiac shift and a cardiac drift episodes. We're going to increase heart rate and we're going to change vasoconstriction to move blood to where blood needs to go. We're going to increase the diameter of the bronchioles via bronchial dilatation. Everywhere else, we're going to change the way in which we're going to be utilizing our fuels. We're going to glucose spare. So we're going to free up lipids so that we can use those lipids. We're going to break down glucose storage sites so that we can get glucose to the cells that need glucose, the glucose obligated cells. immune cells are going to increase their overall function and increase their inflammatory responses. Hopefully, we're going to get enough change to eliminate the stress, but until we eliminate the stress, we keep going and keep going and keep going. We're going to see the same exact function going on with the next hormone we're going to look at, cortisol. Cortisol, same exact signaling here, except instead of being an acute response, we're now looking at a chronic response. And by chronic response, we're talking about a couple of hours. Notice we're going to almost all of the same tissues we went to before. We're going to signal a glucose-sparing event. This is one of the reasons why cortisol is sometimes referenced as a glucocorticoid. This is going to be part of the counter-regulatory response to glucose homeostasis, where we're going to increase lipid mobilization, we're going to decrease glucose utilization. We're going to free up amino acids so that we can involve the amino acids in the energetic pathways. We're going to change the inflammatory responses. We're going to become functionally more specific to the exact response that is necessary. Cortisol itself, in terms of the proteolytic functions, loves to break down collagen. And because it likes to break down collagen, we have to worry about excessive cortisol responses in response to a physical stress. Okay, the last bit of response we're going to get gets tied in with a whole bunch of other pathways, and we'll look more involved at this when we look at blood pressure regulation. But let's look at it in terms of the mineralocorticoid, in which we have an elevating level of potassium in the plasma, or a dehydration signal, which is going to lead to an increase of aldosterone. This increase of aldosterone is going to increase the potassium excretion while increasing sodium reabsorption. It uses a sodium-potassium pump action and an aldosterone-specific potassium transmitter in order to alleviate the potassium load within the plasma. A secondary signal that can come into play is a dehydration or a low plasma volume signal. What this is going to do is this is going to lead to a reabsorption event of water combined with a vasoconstrictive response. So aldosterone has two specific functions here, but the principal function it's going to be doing is regulating potassium levels secondary to the changes of fluid levels. So the last one we're going to be looking at here are the hormones coming from the pancreas, and the hormones coming from the pancreas are going to be found within the islet cells. Those are the alpha and beta cells and the delta cells. Now, in terms of pancreatic function, it's going to have both exocrine and endocrine functioning. Roughly 99% of the cells within the pancreas are going to be utilized for digestive functions, and these are the acinar and F cells, which are going to be secreting all of the pancreatic digestive juices. We're going to look here at the islet cells, and the islet cells, or the islets of Langerhans, are the alpha cells responsible for secreting glucagon, the beta cells responsible for secreting insulin, and the delta cells responsible for secreting somatostatin, which is going to regulate insulin and glucagon. Insulin is going to be released in response to feeding, thinking about food, any sweet sensation within the mouth, responses to exercise, stress, and beta cell stimulation off of a glucose-sensitive GLUT2 transporter. Insulin itself is a peptide hormone that's going to regulate GLUT4 transporters. The GLUT4 transporter is responsible for increasing the uptake of glucose at specific cells within the body, skeletal muscle, adipose tissue, and the liver. At those tissues, it's going to initiate synthesis of glycogen, synthesis of lipids, and synthesis of proteins. It is sometimes referenced as being a ubiquitous anabolic hormone. Glucagon. Glucagon is a counter-regulatory hormone, which means it's going to act antagonistic to insulin. It's going to activate the breakdown of glycogen It's going to increase the gluconeogenic pathways in the liver. So let's take a look at how these two hormones are going to counterbalance each other as it relates to glucose homeostasis. So we start with feeding behavior. Feeding behavior is going to increase sensation of foods coming into the mouth. This is going to stimulate the beta cells, particularly once we start stimulating the beta cells via the GLUT2 transporters, because we start sensing carbohydrates and lipids in circulation. This is going to initiate an insulin release. The insulin is going to immediately feed back on the beta cells so as to not over-release insulin. At skeletal muscles, we're going to increase protein synthesis, increase glycogenesis, and increase lipogenesis. At the liver, we're going to increase glycogenesis, we're going to increase lipogenesis, and at adipocytes, we're going to increase lipogenesis, all in an attempt to get the circulating levels of metabolites down. This leads to what's referred to as hypertrophy of the tissues. As we start to uptick the transport of metabolites into the cells, or if we have an excessively long fasting, and by excessively long fasting, we're talking somewhere between 3 and 5 hours, we start to drop carbohydrate levels within the plasma. As carbohydrate levels drop, the alpha cells will get stimulated to release glucagon. As glucagon gets released, it will inhibit the alpha cells. It will stimulate the skeletal muscles to produce glucose by breaking down glycogen via glycogenolysis. It will stimulate the liver to break down glycogen via glycogenolysis, and will stimulate the gluconeogenic processes in the hepatocytes so as to increase carbohydrate levels. The other thing that glucagon can do is it can increase lipolysis in those same tissues, as well as stimulate adipocytes to release lipids via lipolysis so as to increase lipids within the plasma. Now, we usually talk about these hormones as it relates to glucose homeostasis. It only functions when glucose is excessively low, and by excessively low, we're talking less than about 60 milligrams per deciliter, or excessively high, and by excessively high, we're talking above 110 milligrams per deciliter. Other than those two extremes, the tissues of the body do not need insulin to take in glucose or lipids or amino acids, and they do not need glucagon in order to increase gluconeogenesis or glycogenolysis.